Hello, everybody. Hi. Today, I think we will have Seraphim as well. I don't see him, but I think he will be here for the second hour, okay? And yeah, I just want to talk with you, to have a chat. So you know him, you already know me, so it should be okay. So I think everybody's here, so we can start. So in the last lecture, we saw the history of computing, right? And okay, the message that I wanted you to have from the last lecture is that history of computing is the history of symbol manipulation. Okay? The understanding that you have two systems. One is a symbolic system, and one is the meaning system. Okay, and if you give your symbols the same structure as the meaning system you're trying to symbolize, okay, you can do manipulations, and the results you get out of that, you can map to the semantic system. What does that mean? That to do mathematics, for example, I can have a clear intuition of the meaning of numbers, for example, right? And I have a set of symbols. I give the symbols the structure of, for example, of arithmetic, okay, on natural numbers. And I do manipulations, just mindless manipulations of these symbols. And I get results. For example, I can write 1 plus 1 equal 2, right? And they're just symbols, they're just signs on a piece of hardware, a piece of paper. But manipulating them using some algorithm, I can reinterpret the results out of that and get back to the meaning, to the semantic system, okay? And we saw how that developed in history, okay? So first, humans, mankind, understood that it is possible to create symbols, okay? It is possible to do signs on paper and to create a connection in their mind between that sign and some physical reality, okay? After that, it's a story of more and more abstraction from that. So first they realized, okay, these symbols don't have to symbolize exactly one object. So one symbol, one object. But I can use a little set of symbols and symbolize many objects, okay? And then they had to realize, wait, after I did that, I can apply manipulation to the symbols. And how weird it is, I get something that is actually meaningful in reality, okay? And okay, we saw the key players. We saw, for example, Leibniz. Well, we saw the Greek people who actually kind of asked the big questions about language, because our language is symbolic, of course, right? So they asked, what can we do with this language? Then a key player that I will expand on him today, let's say, was Leibniz, okay? He understood, wait, so we have this set of symbols. Maybe we can express all of mathematics with that. Maybe we can do all of computation, okay? We can express everything. And we can create a machine, okay? Because it's mechanic. You don't have to put our mind to do this computation, okay? We can create a machine which can output all of mathematics. You give this machine a theorem, and the machine reads the theorem, applies some mechanic symbol manipulation, and it says, okay, this theorem is true. Okay, this is a true theorem in mathematics. Okay, this is a fact. This is true. Okay. And Leibniz thought that was possible, and he started to actually try to work out how that language could be derived. Okay? Oh. And today is really the continuation of that thought. I will talk about Hilbert. I started talking about him in the last lecture because I forgot the order of the slides. And so basically, if you remember from last lecture, we finished with the Industrial Revolution, right? We saw Babbage. We saw how communication developed using electric signals with Morse. And so today we start with the end of the 1800, the 19th century. So what happened then? As you recall, as you may recall from the last lecture, there were these two guys discovering that space doesn't have to be Euclidean, okay? They saw from the axiomatic system that Euclid built that if you relax some axioms, you get out some geometry, which is not Euclidean, okay? So it's not, the space you build with this geometry is not the same space that we feel normally, okay? Intuitively. And they saw that there was no way to decide if the space we live in is Euclidean or not. Because many spaces are actually locally Euclidean, right? And so from that moment, okay, mathematicians started to feel a little bit of heartquake on the ground they were walking. They were starting to think, okay, maybe this mapping between reality and mathematics, maybe we shouldn't really give it for granted, okay? Maybe our intuitive understanding of mathematics is, we cannot rely on that to build our mathematics. Maybe we need something more formal, okay? In fact, in the end of the 1800s, on the first slide, exactly that, Hilbert, which was a great mathematician at the time, he made a program, okay? Actually, I'll write it down. Okay, so Hilbert looks something like this. The guy with a beard. Okay. Say, okay. Sorry? Okay. I have to learn. Yeah, maybe it was better before. So what he said is, okay, now we know, we know we can build formal systems. What's a formal system? A formal system is a system, okay, you have a set of symbols. Symbols. And in this set of symbols, you have symbols. So, I don't know, a star, X, for every, exist, okay? So just symbols. And then you have a set of rules. Okay, so telling you how to combine these symbols, okay? So for example, you can combine a star with an X, and then after that you can put, okay, it's a set of rules, telling you what you can do with the symbols and what you cannot do with the symbols, how to combine them really, okay? If you have that, you can build formulas. Okay? So you can build an infinite set of formula. What's a formula? What symbol combinations, okay? 1 plus 1 equals 2 is a formula. For each x in a set x squared, okay? That's another formula, okay? So you can build these formulas. And what Hilbert wanted, okay, given such a system, let's find, first let's find these symbols and these rules. And after that, we create these formulas. We choose a set of axioms. Axiom 1, axiom 2, axiom 3. Okay. We do just 3. And combine them to produce propositions. Proposition 1. Maybe you can combine these two to do a proposition 2. Okay? So what he wanted is a system where you can do this. So you have your symbols, you have your rules, you build up formulas, you choose a subset of these formulas. You choose, for example, I don't know, 7 formulas, and you say, okay, these are axioms. And then by these rules, you can combine the axioms and create propositions, which are just strings of symbols, right? And what he wanted is a system which is complete. consistent. And then it wanted also it to be decidable. Now I'll explain to you what these words mean, okay? Decidable. Okay. So what does that mean? Okay, well, let's start with consistent, which is the property which is the easiest to explain, okay? So a consistent system is a system where you cannot derive a proposition and the negation of that proposition, right? If you study just a little bit even on mathematics, okay? If you can prove something and the contrary of something, then your system is crap. You cannot do anything with that because it means that you can prove everything and the contrary of everything, right? Nothing you do has value, has meaning, okay? Because whatever you derive is just, you can derive the opposite, so there's no value to that system. Now, okay, so this is a formal system, okay? Formal. What does this mean? That until now, there's no meaning in it. Until now, it's just, I tell you what are the symbols, I tell you what are the rules, you combine them mindlessly and you get propositions, okay? But there's no meaning. The nice things about formal systems is that you can give meaning to that, okay? So you choose something for which you read out these axioms and they say, okay, if I interpret this symbol like this and I interpret this symbol like that, then these axioms make sense. They say true things about my semantic system, okay? So for example, if I had, I don't know, 1 plus 1 equal to as symbols in here, they're just strings of symbols. But then I apply the meaning. So I say 1 is this, 1 is this, and then I combine and I have 2, right? So now, when you apply your meaning, when you put your meaning in this formal system, you can say that statements are false or true, right? So you read out the string and you say, okay, I'm talking about arithmetics, for example. 1 plus 1 equals 0. That is false, okay? That is something that is not true. It's a string of symbols which is not true in what meaning I want to give them, right? So what Hilbert wanted is a system, a formal system, in which you could express all of mathematics with the system. So whatever mathematical theorem, for example, you want to express, you can express in this system. Using these axioms, you combine them and you get a nice theorem. And he wanted all the true formulas to be derivable from the axioms, okay? And all the false formulas to be not derivable. So, for example, here I have some symbol combination which is a legal combination. For example, 1 plus 1 equals to 3, okay? It is legal, okay? If you read it out, okay, 1 plus 1, the plus, you can combine with two numbers, the equal, you can put it there, the 3, you can put it there, there's no problem formally, okay? But it is false, it is not a true statement. So, when Hilbert says complete, okay, he wants a system for which all the true theorems, all the true propositions follow from the axioms, okay? And he wanted also it to be sound. I want to explain why. Okay, sound meaning that you cannot derive a false statement from the axioms. Okay, which is the basics. Because if you have the axioms and you derive a false statement, you can throw your system in the bin. It's useless. Okay. So complete, consistent. Okay. So you wanted that, and and he wanted the system also to be decidable. Meaning what? He was completely convinced, okay, at that era everybody was pretty much completely convinced that mathematics was mechanizable, okay? You just had to find this system. So some genius will come and say, okay, Hilbert, I really like your idea. I built this system. I prove that it's complete. So all true formulas can be derived from the axioms, okay? I prove that it's consistent, so I cannot prove something and the contrary of something. And decidable. What does it mean? Well, decidability is what Turing will work on later, and it means, okay, if I give you a theorem, okay, or sorry, if you give you a proposition, so I give you a string of numbers, of symbols. I give you a string of symbols, and you tell me if this string of symbols derives from the axioms, right? So can you combine the axioms to find the string of symbols? Because if that is the case, and the system is completely consistent, you can say, okay, computer, I have this theorem in mathematics. I have no idea if it's true or false, okay? For example, well, I don't know, some theorem on prime numbers. After 1000, the prime numbers have a spacing of 3 numbers. You cannot find 2 prime numbers which are nearer than that, okay? I just made it up. It's probably false, okay? So you shove that into the computer, and Hilbert wanted a system which is decidable, meaning that the computer will tell you, okay, I tried to derive this from the axioms. Okay, I derived it, it is true. Or, no, I didn't derive it, so it must be false, okay? So for every mathematical theorem, the computer could tell you it is true or it is false. And everybody in that period was convinced that that was possible, okay? That you could build this language to encompass all of mathematics. All you could say with this language had to be true. And yeah, that would fulfill Leibniz's dream, okay? He wanted to do exactly that. He wanted that. And Hilbert basically just repeated that, formalized it, okay? Okay. Okay, there was a problem though. He wanted this system. Actually, there were. I'll show you the slide now. Okay. Oh yeah, you have also this property. There's no axiom which is derivable from the others, but it's okay. So after he proposed this program. Some people try to fulfill it. Okay, some people try to build the system. And the most famous attempt to this, to the formalization of all of mathematics, was the one from Bertrand Russell and Whitehead. They wrote the Principia Mathematica. And if you remember, in the last lecture I told you the title of another really key book in the history of mathematics, which is the one from Newton, which is Philosophiae Naturalis Principia Mathematica. Okay? So when Whitehead and Russell wrote that book, they were saying, okay, this is the next good thing after Newton. Okay? So Newton did that, okay, it's great, but hey, we formalized all of mathematics, okay? If you think, okay, he basically built a formal system as I showed you, and he and Whitehead said, if you take the rules on this book, okay, you can build all of mathematics, okay? So why did he bother with that? And why Hilbert wanted that as well? Because, as I told you, in that period, mathematics was on trembling ground, okay? Because there was this new geometry, non-Euclidean geometry, was born, okay? Einstein was saying really weird things about the nature of space and time, and actually there were quite a bit of statement in mathematics that were quite paradoxical, okay? Now in natural language, they will sound something like that, okay? So there were some statements which you couldn't make sense of them, okay? So mathematicians were, we need a system which is, you know, stronger than that. If we have to fund, you know, to build a foundation for mathematics. Otherwise, you know, we're building from nothing, and at a certain point we build this nice castle of mathematics, and someone can just take it down, okay? So here we have some nice paradoxes. One is the Russell. Well, it's called the Russell's paradox, but actually Russell in his Principia Mathematica solved it, let's say. So it built a system in which this kind of paradox couldn't be built. So the paradox, I don't know if you know it, is like I have a set of all the sets that do not contain themselves. Does this set contain itself? If not, then it should. If it does, then it shouldn't. So it's a paradox. Okay, it's like a circular. You know, you're trapped in a tornado of logic, and you cannot escape. Okay, this is famous, and this paradox, Turing will use it to prove. I just turn this down. Just turn it off. Doesn't work really. So it's the same, right? You can hear me exactly the same as before. So Turing used the liar's paradox to prove that the decidability problem that Hilbert was proposing. Okay, so Hilbert was asking, can we build a computer so that you give this computer a proposition and the computer says this is false, this is true? Okay, seriously, I thought it was so Turing showed that was not the case. You cannot decide. You cannot build such a computer, and I won't explain it today because it's something I'll leave for the end of the course when we meet. We actually made the Turing machines. But he used this paradox. So these guys, this mathematician, wanted to take the paradoxes out of mathematics, but it's like they shot it out the door and they were coming in by the window, okay? You really cannot build this formal system which is void, in which you can't build paradoxes. Whatever formal system which is expressive enough, okay? So it's not a... You can do quite advanced things with it. We'll have paradoxes, okay? So now, the guy who started all of this, and who actually, so from Kurt Gödel, right? He took Hilbert's questions. He took Hilbert's dream, and he just destroyed it. Okay, so Hilbert clearly wanted this system, which is consistent, complete, okay, and desirable, and Gödel just didn't, didn't want to just destroy this dream, basically, okay? And what he did was, okay, for every, he proved, so he proved two theorems. I don't know if, okay, it's probably better if I do it here. If you have a system which is powerful enough to express even just a little bit of arithmetics, you will have paradoxes in it, and I'll show you why. So basically what he did, he built a statement which sounds like this. This statement doesn't follow from the axioms. Okay? So he took the symbols from that formal system, so that. And he just built this proposition. So we don't know if it's true or false. We don't know if it follows actually from the axiom. So does it follow from here? We don't know. He just built it. Okay. I can say this. If you give me a formal system which is strong enough, I can say this. I can build this this sentence. Okay. Then he said, okay, we have two possibilities. Either it's true or it is false. Right? Makes sense. So when you give meaning to your formal system, you can say this is true or this is false. And then we have other two possibilities for each truth value. Either it follows from the axioms, or it doesn't. doesn't. Follows, doesn't. Okay? Now it says, okay, well, let's exclude the possibility that it is false and it follows from the axioms. Because as I told you, we want a system which is sound, right? So if it follows from the axioms, we really want it to be true. Because if it falls from the axioms, you can prove stuff which is false. Just, you know, your system is correct. So just, okay. So let's examine the other properties. So this statement doesn't follow from the axiom. It is true. So it doesn't follow from the axioms. Well, but if it follows, then there's a contradiction. This means that the system is inconsistent. So you can prove contradictory stuff. You can prove something and the negation of that. Okay? Okay, let's say that it is false and it doesn't. So it's false. This statement doesn't follow from the axiom. It's false. So it follows from the axioms. But it doesn't. Okay? Again, another contradiction, inconsistent. Your system is inconsistent. You have another possibility, which is that the statement follows, it doesn't follow from the axioms, and it actually doesn't follow from the axioms, okay? But in that case, you have a true statement which doesn't follow from the axioms, okay? If you remember the other diagram, you want all the true statements to be here, okay? So you want all the true statements to follow from the axioms. And he proved, okay, either you have an inconsistent system, or, okay, you have an incomplete one. So you have some incomplete one. You have some true statement which doesn't follow from the axiom. So it's here, in this side of the diagram. So he completely dismantled Hilbert's ring. So he wanted a system which is complete and consistent. But you have to choose. Either your system is incomplete or it is inconsistent, okay? And that is true for every formal system which is powerful enough to express just a little bit of arithmetic. So I think is addition and multiplication. If you can do addition and multiplication and you have numbers and you have some quantifiers, you already can do that statement, and already your system is either incomplete or inconsistent, okay? So that really shaped the mathematicians' world, because now they know that whatever language they can come up with, it's flawed. You can find a paradox in that. And that is like you can't win. And he went further, and he proved a second theorem, which is even more mind-boggling, which is. Okay, let's say that you can use your formal system to prove that your formal system is consistent, okay? Because you want that. So you want a language that can express all of mathematics. So you want a language that can say, okay, this language is consistent. So this language will never lead to a contradiction. So if you can do that, so if you can say, this formal system can never, let's say, is consistent, just that, consistent. Let's say that you can build this statement in your language, right? Well, but there's a problem here, because as Gödel proved, okay, if your system is consistent, then it has to be incomplete, right? But, okay, so, one important thing that I missed out is that axioms, this statement must be built from the axioms to be true, right? So, your formal language, if you want to build that, you have to build from the axioms, okay? But if this formal system is consistent, you're ruling out these things that already have been proven, and you're left out with only one chance, okay? that this statement is true and it doesn't follow from the axioms. But that means that you can prove that this statement, blah, 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 but this means that this statement follows from the axiom, so you found a contradiction. So you're saying, if your system is powerful enough to prove itself free of contradictions, then you have contradictions, okay? So you can't win, and you can't break even. Break even, okay? So Gödel completely destroyed the Hilbert string. Now, the good thing for you is that you don't have to know this. I just wanted to show you because it's awesome. So, it won't be on any exams. I see that you're relieved. But, yeah. I mean, this stuff is as powerful as what Einstein had shown, right? But nobody knows it because it's actually a little bit advanced, so you cannot teach it in high school. But it had the same power on mathematics than Einstein and quantum physics had on physics. So it's really a pity that nobody knows about this result. So now you know that it didn't exist. Okay. So Gödel did just that. Okay. At the same time, there were engineering. There was an engineering progress, right? So Toszek invented the drum memory, which would be used a lot before we come to our hard disk. And well, it was the first kind of memory which was really suitable for the huge the huge computers that they were building at that age, right? So the drum memory is exactly a drum. You had heads that could read and write, and the drum just rotated, and you could access information that way. Okay. Zuse was the first. So he built the first electric computer, not electronic, electric, meaning that it worked on electricity. It was still mechanical. It wasn't Turing complete, meaning that it wasn't as powerful computationally as our computers or as a Turing machine. But it was a huge progress for computer engineering, because this guy already had figured out many things, like that the most convenient way to do arithmetics is with floating point arithmetics, that the most convenient system of symbols to be used in a computer is the binary system, okay? And actually I think we have a video on this guy. We will see it.
The first moves toward changing the meaning of the word computer took place here, in Berlin, in the early 1930s. A young engineering student, Konrad Zuse, took the first steps toward building a computer. He had a limited objective at first. It was simply to avoid hard work.
Ja, das ist ja wohl klar, als ein junger Mensch, der gerne andere Dinge treibt, nicht nur...
Well, a young person clearly has better things to do than study and calculate. A civil engineer has other ideas in his head than just calculating, like plans for building bridges. And the calculations involved are not much fun. You could say that I was too lazy to calculate, and so I invented the computer.
Ich war zu faul zum Rechnen und erfand den Computer.
As he thought about building a computer, Zuse realized he needed a completely new approach to engineering design. Most machines, including the airplanes that Zuse was working on at the time, are built of a few basic subsystems, like the power plant, the hydraulic system, wing assemblies, and so on. Each system has a structure completely different from all the others, and once they are assembled, the purpose of the machine is determined. No amount of juggling of systems would turn these planes into cars. But a computing machine would need to be adaptable, like the human it sought to replace. The human computer used simple components, just 10 numbers and a few signs. By moving them about and arranging them in different ways, she could perform a huge range of tasks in arithmetic, from stress analysis to calculating the positions of stars. Zeusa reasoned that for a computer to vary its role to the same degree, it had to be based on a simple element, an element which could be easily replicated and then combined in different ways to produce different outcomes.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
The telephone industry used such a component, called the electric relay, a simple on-off switch. Zeusa realized he could build his flexible arithmetic machine out of relays, provided his machine counted in an obscure system called the binary system, which has only two numbers, 0 and 1.
2, 3, 4, 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10.
Probably because we have 10 fingers, almost all human societies count in tens. It's so ingrained it seems to be the only natural way to count, but there are many other ways. Instead of the 10 digits we use, the binary system uses only 2, 0, and 1. Remarkably, these 2 digits can do as much as 10. The advantage of having only 2 digits is that they can be represented very simply by a switch. A switch in the on position equals 1. One in the off position, a 0.
Binary numbers really came about from an engineering standpoint, because to an engineer, nothing is simpler than a switch that has basically 2 positions on and off. Compare that to the decimal calculators and the machines that Babbage tried to build, which had 10 positions, and you come away with an instant regard for the elegance and the simplicity of what later became called the binary system. But to an engineer, it was just a simple, let's build the simplest element we can. What is that? That's a switch that's either on or off.
Arithmetic could thus be carried out by circuits of electrical switches. Binary numbers, zeros and ones, could be added and subtracted. But to add just 2 binary numbers, 1 and 1, it takes 4 relays. So Zeusa realized that to do significant arithmetic, his computer would need hundreds of switches. Zeusa's experimental machines filled the family's front room. They looked crude, but using his parents and university friends at labor, Zeusa solved most of the basic design problems. In 1939, he was the world's leading computer designer. Zeusa's dreams were interrupted by the outbreak of the Second World War, a war which would change the computer from a small private venture into a large government-funded enterprise. He was drafted into the Army and served for 6 months before he was discharged when it was realized he could do more for the war effort as an engineer than as a soldier. With the help of military funding, Zeusa completed 2 more computers using telephone relays. And to program them, he ingeniously got around wartime shortages by punching his program into rolls of discarded movie film. By the end of 1941, Zeusa had succeeded in building the machine which Babbage had dreamed of 100 years before. He had a programmable general-purpose computer, and time would prove that the structure he chose and the use of binary arithmetic were the right solutions. But the relays meant that his machine was still too slow to be very useful. It took 3 to 5 seconds to perform a multiplication. There was a faster switch available. The vacuum tube was the foundation of the new electronics industry. Vacuum tubes were most commonly used in radios where they acted as amplifiers, but they could be used equally well as lightning-fast switches. One of the friends who had helped Zeusa build his first machine, Helmut Schreier, believed that the future of computers was electronic.
He came to my workshop and said, "You ought to do this with vacuum tubes." I thought he was joking at first, but we thought about it, and the idea that you would be able to calculate 1,000 times faster was magic.
In an electromagnetic relay, the switching is done physically by a piece of metal that must move from one set of contacts to another. In a vacuum tube, the switching is done by electrons, which for all our purposes can be considered to have no mass at all, no inertia. You can switch them very rapidly simply by turning on or off another current. That in practice means that you get switching speeds around 1,000 to 2,000 times faster than the best relays.
Excited by the prospect of a fantastically fast machine based on vacuum tubes, the two young men laid their plans. They calculated that working together it would take them 2 years to build an electronic computer. But when in 1941 they put in a request for funding, the German High Command turned them down. Hitler had decided that no long-term projects should be undertaken. The war, he said, would be won in much less than 2 years.
At that time, it seemed obvious that 2 years was too long. So nothing became of electronic development in Germany.
It's always about money. They did the same with college, if you remember, right? He never completed his computer because they cut the money, and that was the same with Zeus. Well, Zeus had built his computer, but he was able then to build an electronic one, and he couldn't, of course, because of it. So now we come to Alan Turing, right? We owe computation theory to Alan Turing, right? So Gödel was the one which showed how well, he showed the first limits of computation, right? Because as I told you many times, computation is just symbol manipulation, right? So we showed that you cannot just express everything with symbol manipulation. You have limits. And Turing completed that discourse, right? He showed that you cannot have any computer deciding with a general algorithm if a statement in mathematics is true or false. Okay? And well, he did, of course, much more than that. So in the meantime, his Turing machine. It's thanks to the Turing machine that we have computers now, because as John von Neumann accredited to him, his theory is really the basics. It is the basis fact from which we can build computers. There's a description here of the Turing machine, but I think we have a video later showing what a Turing machine is. So if you're curious, now we can see it. It was one of the first, or probably the first real proponent of artificial intelligence, meaning that in the beginning he was, because he could see that every computation, that every digital computation could be done by this Turing machine, he thought that the power of this Turing machine was absolute. So you could create intelligence out of Turing machines, right? You could create intelligent machines, okay? And he also, well, you should know the Turing test. He proposed this Turing test, meaning that you put a person in a room, and then in the other room you could have a computer or a person, and they communicate with the means of something which you cannot determine visually or with any other sense if there's a person on a computer, right? So they communicate via text, via symbols, okay? And the person in the room has to understand if in the other room there's a computer or there is another person, right? And this test has been surpassed, has been passed actually many times lately. So it has been done, this test, to see if humans could be fooled. If humans could be fooled by a computer, okay? And it worked. For example, we have chatbot, Cleverbot, which is a chatbot. I think it passed the test some time ago. But if you think that's real intelligence, then I have a Yeah, but bad news for you. That's not real intelligence. In fact, I think, and certain things as well, that in the end, Turing really saw the limits of what could be done with digital computing, because in the end, he began working on computational biology. Okay, so he started working with chemicals and pattern formation in chemicals, which is really analog. Okay, it's not digital stuff, okay? So it probably, in the end, he wanted to find a way to go further from this digital computation thing. Of course, he couldn't, because he died. He was homosexual, and society at that time didn't really like that. And he was forced to take estrogens, because that apparently could cure him of his homosexuality. And so he decided to kill himself, apparently, with an apple, a cyanide poisoned apple. That's so a little video about Turing and his life.
In 1936, Germany hosted the Summer Olympics under the dictatorship of Adolf Hitler. This event supplied an opportunity for worldwide Nazi propaganda to be distributed prior to World War II. In this same year, 24-year-old mathematician Alan Turing invented a theoretical machine that would change history in a comparably significant manner. He names it the Turing machine. The basic parts of a Turing machine require a tape, a head, a table, and a state register. The Turing machine requires an infinite amount of tape where symbols may be written and erased. The head is to read and write symbols. This example reads the information with the camera and writes information with a dry erase marker. This is a table of instructions. It carries out the commands and tells the machine when to erase or write. It also moves the head left or right and assumes a new state is prescribed. This action is represented by a control pad. The state register stores the state of the Turing table. It is intended to replace the state of mind of the human operator. This example uses memory cards that hold text files of instructions to be carried out by the table. The symbols in this machine don't necessarily have to be numbers. They could be anything. The idea is that anything that can be written down and converted to symbols has the potential to be carried out by one machine. September 1st, 1939, Hitler invades Poland, marking the beginning of the Second World War. At the start of the war, Nazi Germany employed a tactic that was virtually impossible to defend against. This attack engaged a complex procedure where German submarines were being guided to their target by encrypted radio instructions. These messages were coded and translated with a highly sophisticated device, the Enigma machine. The Enigma machine can be broken down to its four core functions: the keyboard, the lamp board, rotors, and the plug board. The keyboard is where you type the text you would like to have coded or decoded. The lamp board displays the ciphered text. If I type an X on the keyboard, the lamp board displays an S. For added security, there are four rotors that move with every entry of a character. Each of these rotors must be placed in the specified order to be correctly coded or decoded. If the rotors are not in the same place, when I type the X this time, the lamp board shows a G. The plug board was the final security feature which affected how the keyboard communicates with the lamp board. Much like the rotors, these wires must be plugged into the proper channels in order to obtain the desired result. It was understood that the Germans could very well have won the war if these codes would continue to be effective. The English government dedicated a group of mathematicians and cryptographers to crack this code. The team was headquartered at a secret facility in Buckinghamshire, England, known as Bletchley Park. Alan Turing, now age 27, was asked to join the team. Turing accepted the challenge and was able to solve the Enigma code within the first few weeks of his arrival. Turing's solution to the German code required inventing an electromechanical device known as the bomb machine. This machine simulated the Enigma machine and was able to manufacture all possible scrambler settings. The bomb employed a new frame of thinking that is now known as heuristics. Heuristics is an artificial intelligence term used to cut down the amount of searching required by a machine. It wasn't precise, but was accurate enough to be useful. Operators understood its instability and were encouraged to try settings that were in the vicinity of the base position. It was understood that cracking this code contributed greatly to the Germans' loss in the Second World War. After the war, Turing was able to focus his work on future technologies. He believed intellectual activity consists mainly of various kinds of search. Alan Turing looked at computers as if they were children. Children are able to absorb information, so why not computers? He dreamt of a program where you could type in words, and then the machine would be able to type and print those same words. Then he thought, if a machine could do that, perhaps one could type in words and the computer could be programmed to type a response. This would act as a pretend conversation with a machine. And if the machine were even more powerful, you might be able to have an actual conversation with it. Better yet, perhaps the machine could become sentient. At this level, Turing thought that turning the machine off might be considered murder. Turing referred to this concept as machine intelligence, which is commonly known today as artificial intelligence. Alan Turing's contributions to society and science have just as much relevance today as they did in his time. The terms Turing-compatible and Turing-equivalent are still used in present time. Each and every modern computer is considered to be Turing-equivalent. Today's machines increasingly become more powerful, yet they continue to follow the guidelines expressed by Turing almost 80 years ago. Alan Turing continually challenged his own theories. He set forth challenges for himself, and more importantly, for future inventors and scientists. His most famous challenge is known as the Turing test. To this day, it is yet to be matched. An example of the test places a computer in one room and a human in another. The two are then required to communicate with one another. Let's say the human and computer are communicating in a chat room. Turing's test insists that the human believe that they are communicating with another human, not a computer. This experiment must be repeatable and random. Once Turing's desired result is achieved, a computer will have successfully obtained artificial intelligence. Turing not only created challenges for his peers, he was known to challenge himself. He would create examples of equations that could not be solved even by his theoretical machines. This study showed his value for human thinking. But more importantly, Turing was suggesting that these are the very issues that must be resolved before machines can truly think like humans.
So he did quite a lot for us, and apparently he is the reason why we won the war against the natives. I think that the documentary is a little old because I'm sure that some software lately beat the Turing test. I remember reading about it, I think it was last year. But the software used to beat the test. Basically, they used a little trick, which is the chatbot presented himself as a 13 years old, right? So all the quirks, could be explainable by the human reading the text, like, oh well, it's just 13, it's just, and but it was fast. So the key facts in computer science are somehow always related to Turing and his Turing machine, right? So, okay, that should be clear by now. Okay, with a Turing machine, okay, you implement algorithms. you implement algorithms, right? But the way Turing showed that you can do that is by inventing a fantastical machine, inventing something that was not physical, okay? He showed the steps you have to do computation. So he clearly showed that there's a divide between hardware, so that the actual physical realization of your Turing machine, and the software, which is the description of the computation your Turing machine is doing, right? Second key fact, all that is computable, computable in, let's say, digitally, okay, so with symbols, can be computable with a Turing machine. I think that is known as a Church-Turing thesis, and so this really gives you the idea how powerful the Turing machine is, right? So everything that is computable with digital computation is computable by Turing machine. So all the limits I told you about are the limits of digital computation, not the Turing machine. The Turing machine is the best you can do with digital computation. But you can do other stuff if you don't use digital computation. So, this is a fact that we will use later, when I will show you how Turing solved, so how Turing gave an answer to the Entscheidungs problem, so the decision problem I told you about, that Hilbert wanted an answer to that. And if you get something from this course, is that all physical computers, all digital computers, all programming languages, the best they can do is be Turing complete, okay? So the best they can do is Turing computation, digital computation, okay? You can go further than that. So when somebody tells you, yeah, this programming language is more powerful, well, it can be more powerful, meaning that maybe it's easier to learn, maybe it's easier to do some things with it, okay, in respect to other programming languages. But as computation power, they're basically all the same, okay? Whatever programming language you use is 99% it is Turing probability. 99% probability is Turing complete. If it's not, it means that you cannot do very much with it. Of course, there can be application to those kind of languages. But normally, if you see C++, I don't know how you use Python, for example, if you use Java, they're all Turing complete. So they have all the same computational power. It's not like you can do something with Java that you cannot do with C. Okay, I hope this is clear. Okay, programming is synonym of term rewriting, meaning that, well, it is exactly the fact that I've been telling you over and over. Computation is just manipulation of symbols, okay? So you take a string, for example here, you want to prove a theorem, you grab the symbols of the theorem, you rewrite them, so you substitute, and you end up with another string, and that's the answer of your problem, is your computation. Computation is just that. Okay, hi guys. Today we're going to briefly conclude on the history of computing, and actually start with the first computing model, which is the DFA, the finite state machines, deterministic finite state machines. So this lecture should be more fun than the previous ones, and I actually can't wait to finish with the history because I'm getting bored as well. So, so in the 20th century, in the last lecture, we saw Turing, we saw Gödel, and the Hilbert's program. You understand where actually computing was born. It was born actually collaterally in the attempt to prove that formal systems in mathematics have certain issues. Okay, but when Turing came up with this model of Turing machines, as Neumann recognized, he actually built a model for computing. Okay, so a model that can actually be used to inform building of computers. So last time we saw Zuse, which built the first electrical but still mechanical computer. And so in this last century, electronic computers were invented, of course, as you know. and this has been made possible by the invention of the transistor. Okay, because in the beginning the electronics was handled by big tubes, okay, vacuum tubes, but they were pretty big, and they got easily broken. But I think you know this stuff because somebody told me that you already had history of computing module, or some part of the module was about history of computing. So I will skip ahead. Actually go straight to the conclusions. What I really want you to know is that, okay, we have this nice model of computing, which is the Turing machine and the universal Turing machine, and it prescribes what we can and cannot compute, what we cannot and can compute. That I told you 1,000 times, so it has to be completely impressed in your head, right? But it is a model about digital computation. So all digital computation that we do and that we will do in the future is bounded to the limits of the Turing machine. You cannot go further, okay? So in the latest news, you see quantum computers, massive parallel processing. What else? There's this new chip by IBM. I think other companies are building this as well, but I know this one from IBM, which is unifying in the same chip memory and processing. Okay, so it's like the brains powered computing. Okay, all these things, if they're symbolic, if they're about symbolic manipulation, digital computation, they all bounded by the limits of the Turing machine. So you get quantum computer. Okay, fantastic. Quantum computers will be super fast. Okay, as I told you last time, if you have a good quantum computer, you just don't care about all the encryption, that we have today. You can crack very easily with a quantum computer. With enough quantum computer, all encryption. Okay, that's why this. Run to the arms for nations, because the first nation that builds a quantum computer have an advantage over the other. Okay, you have access. You have the NSA, square it, cube it. Okay, if you have a quantum computer, you just can have access of all the information you can get. You don't have any problems, decrypting it. So. But what I'm telling you is that, okay, we build this quantum computer. We build massive clusters of GPUs, massive parallel processing with a lot of NVIDIA, Tegra, I don't know what the names are now, the Volta. Okay, you do that, you're still bounded, okay? You still cannot solve more problems with those than you can do with these, okay? You can solve them faster, okay, that's all right. But if you cannot solve one problem with my tablet, let's say, given a reasonable amount of time and memory, you cannot solve it with a quantum computer or with a massively parallel computer, okay? So we have to look somewhere else to overcome these limits. We still don't know if we can overcome these limits. All computation we know today is digital computation. We still don't have a good understanding of or a good framework for analog computation. But if we have a chance of overcoming the limits of digital computation, that has to be found in analog computation. Okay, and we concluded the history part.